Hello student, so welcome to the today's lecture. So today we are going to learn probably the most important theorem uh, in the probability theory. So it is called the Central Limit Theorem. The Central Limit Theorem. Okay, before going to discuss it properly, so let us try to recall the law of large number, what we proved in my last tutorial, last lecture, a rather strong law of large number. So what is that? So you have these IIDs x1, x2, okay, so IIDs, and then we proved that actually you can write down strong law of large number. So what was that? It tells you that x bar, the sample mean, is converts to mu almost surely, right? So that we already proved. Okay, or in other words, I can say that x bar minus mu converts to 0 is almost surely, like that means in with probability 1, right? But one can ask the question that how fast is the convergence, like the rate of convergence. So it is converging very fast, slow, and how do you measure those things, right? So in mathematically, you want to find out that growth of rate of convergence. So this is general notion. So if you want to multiply by a number and then you want to check that whether some in power something whatever with this quantity, whether this converges or not. So if it is going to 0, then you say that this quantity is converged faster than this n power whatever something. So it can be some alpha which is positive. And if it is and you know that if alpha is positive, n for alpha is convergent divergent to infinity. So if the product diverges to infinity, then that means the convergence of sample mean minus the actual mean is slower than the divergence of this, right? So this is the question. So and that question, the solution to that question lies to something called central limit theorem. So that tells you that actually n power half into x bar minus mu, and then we standardize by the standard deviation sigma, that actually converts to a nice quantity which is called standard normal distribution, okay, as n tends to infinity. So what does that mean? That means that this you can think that sample mean has a nice property that this quantity is actually kind of a standard normal distribution. As a distribution, they are same. Okay, so I will write down mathematically this statement. So statement. So now you see that so you can write down this x bar as say x1 plus x2 plus dot 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 xn, this is divided by n, and then mu, and then you want to know that sigma times, okay, so n power minus half this quantity, right? So this quantity is what? This quantity actually, if you now multiply by n, and then this quantity becomes, so that this quantity becomes x1 plus dot 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 xn by n mu, and then sigma into n power half. Okay, clear? So this quantity becomes this quantity. So central limit theorem tells you that this quantity tends to normal distribution, standard normal distribution as n tends to infinity. Okay, this is so you can understand this is very nice theorems. Okay, and this theorem has lots of applications in statistics, probability, everywhere. So what does that mean? That means suppose you have these IIDs. So let me explain it. So x1, these are IIDs. You don't know about the distribution. So these IIDs may not be very nicely distributed. Still, they are. You can think that the sums summation xi, which is my Sn I equal to 1 to n, and so the standardized one, the standardized Sn minus n mu by sigma into n power half. This actually following the normal standard normal distribution. Okay, so if you collect a large kind of sample, no matter what I mean, like what is the sample size, and they follow this kind of normal distribution, standard normal distribution. Okay, on an average, kind of term distribution on an average. Okay, on an average, they follow those things, right? So so this is standard central limit theorems, but in historically it does not like. So let me think about talk about little history. So historically this theorem was not proved in this form, so it was proved in a special case by Abraham DeMoivre. So what DeMoivre proved? So let us discuss a little bit things. So I think this is 1733, something like that. So DeMoivre proved that. So he was trying to start with this Bernoulli and with probability p. So what does that mean? That means it's kind of a coin tossing experiment. So you have a random experiment which has two outcomes, either success or failure, and probability of p is the probability of success, and then 1 minus p probability of failure. Okay, and you would like to know that after n many trials how many success you have. So this quantity Sn, so let me define Sn then. So Sn is what? So Sn is summation xi I equal to 1 to n, which is the number of success in trials. Okay, so you would like to know about how Sn distributed, and this theorem, so this is the idea of DeMoivre, and he proved actually the case when p equal to half, or in this case when p equal to half, the probability of success half. And later on Laplace, another famous mathematician, Laplace, I think around 1812, he extended these results for general phi. Result is proved for general p. Okay, so general p probability is not necessarily only half, it is greater than 0, less than 1. Okay, and what was their theorem? Their theorem is nowadays we call the DeMoivre's Laplace theorem. So what is this theorem? So you have this exercise IIDs, and then Sn is the Sn. So this exercise IIDs. Okay, and Sn is the sum over xi I is 1 to n kind of number of success. Okay, and then for any real number, say a less than b, real number, or rather yeah, so that this quantity Sn minus, now what was, so Sn is kind of a binomial distribution which count number of success in many trials, and the mean value will be np. So that, so I am just standardizing, so I am making it some random variable with mean 0, and then the standard deviation is nothing but root over n p 1 minus p, that is standard deviation of binomial distribution. This quantity is in between say a and b. Okay, so I would like to know that what is the probability that this quantity is a and b, and these probabilities actually following the um, standard normal law. So phi of b minus phi of a. So this was the uh, special case was proved by DeMoivre-Laplace. We call it DeMoivre-Laplace theorem. Okay, and for general case, what we wrote, yeah. So this is the special case. So we will prove the general case for central limit theorems, and then obviously special case will be part of that. Okay. So now start with the general case. So okay, so then let me write down again the statement, the central limit theorem, central limit theorem. Okay, so let x1, xa, xn, and be IIDs, random variables. So identically independent and identically distributed random variables. Okay, and with say mean, so they have common mean because their I is mu, and variance of xi say sigma square. With all those things, the quantity what we described earlier, so this quantity uh, minus n mu and then divided by the variance into base, this quantity tends to normal 0 1. Okay, so this is general theory statement, and that actually we will prove this version, and then it's sufficient to prove the whole DeMoivre-Laplace theorem, right? Okay, now how do you prove this kind of theorem? So you recall that when you learn moment generating function, recall um, um, recall when you learn moment generating function, I told you that generating function, what I told you that this moment generating function uniquely define the distribution, right? So that property is going to help us, and let me write down this lemma which we are going to use of in our proof, which is a property of homogeneous function. So suppose let you have say sequence of random variables, say x1, x2, and dot be a sequence of random variables with cumulative distribution function, say f of xn. So what does that mean? That f of x1 is the distribution function of x1, f of x2 is the distribution function of x2, and so on. Okay, um, and moment generating function. So so let me write down this symbol m x n. So these are the corresponding moment generating function of x1, x2, xn for all n greater than equal to 1, right? This is given, and you have another set of functions, another random variable, say x, b, another random variable with f of x is the CDF, and m x is the moment generating function of x. So moment gen function of x. Okay, so if this is given, then what happened? So then this important then if the sequence of moment generating function m of xn of t converts to the moment generating function of x mxt pointwise. So what does that mean? That means for each t m in the sequence mxnt has a limit mxt, and then the distribution function if xnt converts to the distribution function of x pointwise for all t. Okay, at which the continuity is important, obviously, at which f of x t is continuous. Okay, so this is what we discussed during moment function. That moment function uniquely define the distribution. Okay, and this property is coming from the property of moment function. So this lemma we are going to apply. So what is the general strategy of the proof? Okay, so let me start with that proof of central limit theorem. So what is general strategy? So we will start about okay, so we let me just assume first the special case. So assume that sorry, assume that mu equal to 0 and sigma square equal to 1. So the special case, and then if you prove this thing for mu equal to 0 and sigma square equal to 1, then we can obviously generalize that thing for general mu and sigma. Okay, so this is my assumption. Then what was the version of Mongian function? Then we need to prove that x1 plus xn divided by n power half, that tends to normal 0 1, right? Because mu equal to 0 and sigma equal to 1, and that mu equal to 0 that cancel out, and sigma equal to 1 in the denominator. Okay, so this portion we need to prove. Now note that so this is, you can write down actually nothing but, so we need to prove the summation xi over n power half I equal to 1 to n, that converts to this 0 1 as n tends to infinity, right? This you need to prove. Okay, so the sum of random variables, and the strategy will be try to find out you try to use that previous lemma here for the moment change function of this new random variable xi over n power half, right? Okay, so let's start. 1 minute. Okay, so I have deleted one page. Okay, again I need to write down again because I have deleted one page. This is a proof of central limit theorem. Assume mu equal to 0 and sigma square equal to 1, and then my theorem will be x1 xn over n power half, that converts to standard normal 0 1, right? And so this is nothing but saying that summation over xi over n power half I equal to 1 to n, that converts to standard normal. Okay, and what is given? So given that m of xi are moment generating function of xi, that is given to us. So then what is moment generating function? So the moment so let me use this symbol here. So maybe I can write down this is my random variable y equal to this. So I would like to know what is that moment generating function of moment generating function of y. Okay, so this is we would like to know. So what is that? So by definition, so I know that this is nothing but expectation of e power. Okay, so e power ty, right, by definition. But now we know that uh, y equal to nothing but summation xi over n power half I equal to 1 to n, right? Yeah, now the sum we can take into product because we have exponent part, so we can write down exponent of e power t x1 power n power half into exponent of t x2 over n power half, like and so on, and then e power xn to the power t times n power half, right? And now you note that these random variable x1 x2 xn are IITs, they are independent. So kind of the product of moment generating function is the moment generating function of the product. Okay, so sorry, yeah, so this is yeah, I think you just need to put here. Yes, so this is this. Okay, so because of the IIT's properties, so you have this, and then you can write down this is nothing but, so this is nothing. The first one is what? First one is nothing but moment generating function of x1, but at the point t over n power half, right? Similarly, second one is moment generating function of x power x2 into then t over n power half, right, and so on. The moment generating function of x n and t by n power half, n by half, right? But because x1 x2 xn are IIDs, their moment generating function are same. Let me write down this is say m So I can write down this as m t over n power half. Okay, and then how many times they appear? N many times. So this kind of power n, whole power n. Okay, so my homogeneous function of y becomes um, a original homogeneous function for IITs at the point you are in power half to the power n, right? Now you would like to know whether these tends to the moment generating function of the standard normal or not, which is known obviously. Okay, now to do that, so let us start with this. Let's define that a new function L of t is logarithm of this m of t. M is what? So m is the moment generating function of this IIDs. So m is mgf of xi's, which are IIDs. Okay. So so what does that mean? So so now okay. So there are two things you can do. So one thing is that you can write down then m mg sorry my of t. So this we prove that mt over n power half, okay, to the power n, right? So if you take logarithm both sides, then you'll have logarithm of my of t is nothing but n times logarithm of logarithm of m of t over n power half. Okay, but m of m power half is okay. So this is write down. Let me write down properly. This is m. Okay, and then this quantity we define by LT. So I can write down this as n of logarithm. Okay, so L. So n of L, and then instead of t I have t over n power half. Okay, so the logarithm of homogeneous function of y is nothing but this. Okay, now let us try to find out how this limit look like. Okay, now note that so one thing you need to check. Okay, so this for to check this limit, you see that uh, how this thing look like. What is L of 0? So L of 0 is nothing but logarithm of m of 0. Okay, and homogeneous function by property this is 1, this inner side, so this is nothing but 0. So log 1 equal to 0. And if you want to find out what is L dash of t, now L dash as t is nothing but m dash t over mt, and hence L dash of 0 is what? So this is m dash 0 over m0, right? Um, but m0 is 1 and m dash 0 is the first moment mu, so this is mu over 1, which is mu, and I already choose mu equal to 0, so this is 0. Okay, this is special case, mu equal to 0 case, right? So as mu equal to 0. Okay, now what is L double dash? Try to first do it, then we will understand what is happening. So L double dash of t will be what? So this is will be ddt of m dash t over this, right? So this is what? This is mt whole square. Okay, and derivative of the first, so m dash double dash t into mt minus m dash t and then whole square, right? So if you want to compute L double dash of 0, and then you see that this is a nice quantity because this will gives you m double dash of 0 and then m0, okay, minus m dash of 0 whole square, okay, which is your mean, which is already 0, you know that, and then m0 whole square, right? So what does that mean? So m dash of 0 is you remember the second moment, okay, and m this second moment, and this is 1 and this is mu, which is already 0, and m0 is 1 whole square. So what is the final thing? Final thing is expectation of x square, okay, and you know that this is 1 as um, sigma square equal to 1 and mu equal to 0, right? So expectation x is equal to 1. So now you already get the properties of L, how it will behave like. Now let's come to the place where we need to find out the limit of this. See, we want to find out the limit of this function. Okay. Now what is the limit of this function? So let us now try to find out that. So we want to find what is limit n tends to infinity. L to the power L in t by n to the power half divided by n to the power minus 1, right? Because it was n times this, so that I can write down as this, right? Now you see that the numerator, when n tends to infinity, the numerator tends to so when n tends to infinity, numerator tends to 0 and the denominator tends to 0, so this is indeterminate form, okay. So and how to do this kind of limit? We know that to take limit of indeterminate form, we need to use something called L'Hospital's rule. So I will use that, and L'Hospital's rule tells me that this is nothing but the derivative of the same thing. So what is the derivative of the numerator? So this is first you will have L dash of t over n power half, and then you take the derivative inside, so that will be nothing but derivative with respect to n, obviously. So n power half means okay, so minus half will come out, so t times t will constant here, and minus half, so minus half, and then t power n power minus 3 by 2, right? Yes, and denominator, if it is minus 1 times minus 1 times n power minus 2, right? This is by L'Hospital's rule. Clear? Okay. Now again, now try to make it a little bit simpler form. If I take the simpler form, then what happens? Then this minus get cancelled, so we have L dash of t over n power half, okay, and then into t, and then in denominator you have 2 times 8 power half in power half, sorry, half minus half in power minus half, okay. So again you see that the numerator is again when n tends to infinity, numerator is L dash 0. So what was L dash 0? So let me tell you. So yeah, here see L dash 0 is mu, so that is also goes to 0, right? Numerator goes to 0 when n tends to be 0, and denominator also goes to 0. So again this goes to 0 as n tends to infinity, this goes to 0 n tends to infinity, and again you need to use L'Hospital rules. So So again we using L'Hospital rules, and if you use L'Hospital rule, then this becomes limit n tends to infinity, and when you have n tends to infinity, then you can write down this as minus L double dash after taking the derivative t over n power half n to the power minus 3 by 2 into t square, okay, and the denominator will be nothing but minus 2 times n to the power minus 3 by 2. Okay, so using L'Hospital's L'Hospital rule again. Okay, so now if I simplify this thing, so this becomes limit n tends to infinity, and then L double dash of t over n power half, and then you have t square by 2. Okay, because this n to the power minus 3 by 2 in the numerator get cancelled, and now when n tends to infinity, you see that what is the limit? It is L double dash 0 into t power t square by 2, right? Now what is L double dash 0? So recall L double dash L what is L, yeah, here L double dash 0 is 1. L double dash 0 is 1, and now I use that, this becomes t square by 2 as L double dash 0 equal to 1. Clear? So so what does that mean? That means the original limit what we are trying to find out, it is nothing but t square by 2, and this is nothing but logarithm of our where is this? Yeah, so this is logarithm of our Mohan function, which is actually tends to t square by 2. Okay, so now we know then thus logarithm of m y t is tends to t square by 2, and hence m y t tends to e power t square by 2, right? Clear? And you can recall that this is very known thing. This is so the right hand side, the RHS is the moment generating function of the standard normal, okay, random variable, right? So what do we get? We get that that the moment generating function of y is converts to this, and hence thus y is converts to tends to normal distribution 0 1 as n tends to infinity. Now recall what was y. So y was nothing but summation of xi over n power half I equal to 1 to n, and that converts to normal 0 1. Okay, so this completes the proof for the case when mu equal to 0 and sigma square equal to 1. Okay, now if mu not equal to 0, rather whatever, and sigma say I mean whatever general case, then you write down your new random variable, say maybe x star, say, of I by xi minus mu by sigma, right? Now you check that your new random variable xi's are also IIDs, and their expectation is 0, and their variance of this xi star is also 1. Okay, so now you can apply here, and then you will get the final version of the theorem, which tells you that x1 plus xn minus n mu over sigma into root over n. Okay, so this quantity is actually converts to standard model distribution. Okay, as n tends to infinity. Okay, so that is the end of the proof. Okay, so now though we prove this pointwise convergence, but it's actually this convergence. So note that uh, this convergence is it's actually uniform. So what does that mean? Uniform, that is, does not depend on the point. So it does not depends. I mean, I remember you guys learn uniform convergence, other thing in the first semester. So we know that it depends on the point. Okay. So clearly this is one of the most remarkable results in the um, theory of probability. Now we can have some example, and then you can ask the case when x's are independent but not say. So let me ask this case. So question: what about say x1, x2, xn are only independent random variables? So independent random variable. So what does that mean? So I mean that they are not identical distribution. So their means and variance are not same. Okay. So means that mu I and then variance of xi is sigma I square. Then what happens? Then do you have central limit theorem for that? The answer is yes. So in this case, um, obviously you need some condition. So uh, so 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 if this following condition true, if condition number one, that xi's are uniformly bounded. So what does that mean? That means um, that there exists an m real number m such that probability that the quantity this event has full probability. Okay, so xi is taking value only is bounded portion of real number. Okay, for all I, uniformly bounded. This is not only bounded, this is a uniform bound for all the random variables xi. This is one property, and the second property, property number 2, that this sum of the variance square is finite, equal to 120. Sorry, so this is infinite. Sum of the variance is infinite. If these two condition holds, then you have a central limit theorem for only independent random variable, for independent random variables, and which tells you that the quantity here is xi minus mu. So these you make the origin changes here, and then you need to standardize, normalize by root over of summation sigma I square. You remember some of the variance of the sums, so because it's identity independent. And this quantity, you would like to know that whether this quantity bounded, what is the probability that this quantity bounded by A, and then this is actually converts to standard normal. So what does that mean? That means this is probability of this is actually this mu of A, okay, as it tends to infinity. So this quantity here, okay, they follow the standard normal distribution provided the above two conditions. Okay, so this is the independent version of the standard normal version of the central limit theorems. So maybe let me just ask you some examples. So maybe let me give you examples. So suppose you have say x1, x2, x10. And all of them are IIDs, uniform 0 1 uniform distribution. Okay, and I would like to know the approximate value of, so what is that approximate value of probability that summation xi I equal to 1 to 10 bigger than 6. So what is the approximate value of these things? Can we have the approximate value? The answer is yes. We'll use central limit theorem. So you know these are IIDs and they are uniform, so you know that each of them has a mean which is half, and the variance of this xi is 1 by 12. This you already learned in the class. And the central limit theorem tells me that probability that summation of xi I equal to 1 to 6 greater than 6. Okay, this is what. So these distributions xi minus n mu divided by sigma times root over of n is following the normal distribution, right? Standard normal. So we need to make it in that form. So you can write down xi's and then minus n mu, n equal to 10 and mu equal to half, so n mu equal to 5. So minus 5, and then if you take it minus 5 here, then this portion will be 6 minus 5, right? And then in the denominator, what was that? It was sigma times root over of n, right? So but this sigma square is 1 by 12, okay, variance. So root over of 10 by 12, okay, sorry, 10 by 12. So let me write that properly here. So n equal to 1 to this square root 10 over 12, right? So this quantity will be root over of 10 over 12. So this is central limit theorem gives us. Okay. Now we can easily find out the results. So that means this quantity is approximately converging to. So this portion is what? This portion is 1 minus probability that less than this. So this is screw phi of 1 by this. So that is root over something 1 point this, right? Yeah, so yes, so whatever is that, so this quantity is approximately 0 point, you can find out from standard normal chart, Z chart. Okay, so so what does that mean? That means almost this is 13.6 or 14%, okay, of time that the summation will be greater than 6. Okay, so if you have IITs uniformly distributed, then you want to find out that out of 10 many such thing, the sum will be greater than 6, so the percentage will be almost roughly 13.6%. Okay, so this ends today's talk, but I would like to give you um, some exercise. So let me find out a nice example, a nice exercise for. Okay, so simple exercise. Let me give you your quiz 4. Okay, and you need to submit this quiz 4 is by so deadline is say um, 13th for 12 midnight. Okay, is the deadline. So what is the quiz? So let me write down the question. So let x be a discrete random variable taking values say 1 2 dot, 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 dot. Okay, so what does that mean? That means is taking values inside natural numbers. Okay, and if it is given that probability that x equal to an integer k, this probability is non-increasing, increasing. Okay, it is given in k. So non-increasing means what? It can be either equal or decreasing. Okay, and then so that the probability that x equal to k is bounded by 2 times expectation of x by k square. Okay, clear? So the question, what we ask, that you have a discrete random variables and that taking all the values from natural numbers, and you also given that the probability that x equal to k is not increasing, so it is decreasing in k. So what does that mean? That means so let me write down that it means, so probability x equal to 1, so non-increasing, so either it is decreasing or same, right? So this is greater than equal to probability of x equal to 2. And so on. Okay, this is the meaning of that non-increasing. So with that, prove that this probability is bounded by 2 times expectation of x over k square. Okay, this quiz 5, probably quiz 5, yeah. Okay, So thank you for your attention. Uh, Bye.